love the music, right?
Yeah. Hold on, the mic's on.
I'm not used to the music intro.
Cool.
You wanna? Could you pass me a water? Stay hydrated.
This is probably the fanciest meetup I've been to in a while.
Funny.
Cool. So today we're going to be talking a bit about proof of stake. And so, yeah, I'm going to kick us off. So first of all, could each of you say a little bit about how proof of stake differs from consensus or compare the two?
Yeah, so I think when people talk about proof of stake, they just lump it together with a bunch of different elements of blockchain consensus. And really, when most of the time when now we research consensus algorithms and develop consensus algorithms, we can think of them in two parts. One is the part that decides who is participating in a consensus. So we can call it a validator set. So and that determines who the rules according to which people are chosen to participate. So in proof of stake, it would be the people who potentially with the most stake, or people that stake a bit of the token. In proof of work, it would be the people that put in some work. In proof of authority, it will be some known people. And then there is the consensus algorithm, or the kind of the rules according to which those parties have to interact with each other in order to achieve consensus. And so really proof of stake is really this only this part on top, while there can be many different, first of all, many different types of proof of stake on top and many different consensus algorithms underneath.
Yeah. And so like proof of stake is this kind of anti-Sybil mechanism, and then the kind of general consensus protocol is how do these different distinct actors actually form a coherent view on reality. But I think Vlad has the best probably brand.
Well, but I mean, I don't disagree with any of that. That was all great. So I would say that, like, you know, proof of stake normally refers to an incentivized consensus protocol that's incentivized with what is technically proof of stake, which is like the kind of signatures that correspond to coins that like somehow like people can, you know, prove that you have on deposit or have staked and therefore have a right to produce these particular protocol messages. So, you know, I would say that like proof of stake is like a really general mechanism that, like, you know, like kind of I got interested in well before I understood that consensus protocols were even a thing.
Like, from my perspective, like consensus in my mind is about coming to agreement over some arbitrary bytes. It really doesn't matter what those bytes do. It's just you come to agreement over some messages, let's say it that way. And then proof of stake really is the economic incentives on how you select who's a good, like who should be allowed to participate in that consensus process and who shouldn't be allowed to participate in that consensus process.
And one important thing is that oftentimes the proof of stake layer also handles any sort of consequences of misbehavior or not following the rules of the actual consensus algorithm that kind of prescribes what's the...
And also the rewards for being good.
Yeah. The nice thing, like the weird thing though, is at that point it sort of gets mixed, right? Because some like slashing conditions are inherently from the consensus level, so like double signing is a consensus fault. And so the consensus layer feeds this up into the proof of stake layer. But there can also be consensus faults on the proof of stake layer, such as you're not live anymore, you're not producing you're not producing signatures for the consensus. So, but that's sort of, right, like there can be different incentives at both layers, or different slashing conditions at both layers.
I mean, to incentivize a consensus protocol, you really got to like be in the weeds of that particular consensus protocol. And so like these incentive mechanisms like kind of know about the internals of these distributed systems. And that's another reason why I like talking about proof of stake. It generally is hard because like what distributed system are you talking about exactly? You know, what are you incentivizing in particular? And the game theory and the incentives and all the story will look different depending on the protocol that's being incentivized.
Maybe the simplest way to think about the difference is consensus is about computer science and proof of stake is about economics. In my mind.
Yeah, I mean, distributed systems and mechanism design, to be like more specific, or like distributed systems and like, market design. It's like somehow public consensus protocol is a market for consensus on transactions, provided between users and validators, and so you can also think of it as a market design. So it's like market design game theory applied to like distributed systems.
Awesome.
But specifically consensus protocols normally when we're talking about proof of stake. But there's no reason that it should be applied to that.
But it is important to note, actually, I apologize, David, that there's this thing like hash cache, so sending messages like in a way to kind of reduce spam when you're sending messages. You can actually use proof of stake for this. So a mechanism that Vitalik likes to talk about is, let's say, if I send you a message, I give you the right to burn $1 of mine. And so what this does is you're not going to burn your friend's dollar because there's kind of real consequences to that. But if there's some kind of person who's spamming the network and sending it to a lot of people they don't know, then there's no problem. I'll burn $1 from that person any day. So this is a proof of stake kind of, or a staking mechanism that is not necessarily about consensus.
Mm-hmm. Yeah, and the same for proof of work. Like there is Whisper, for instance, where also the spam on the network is prevented by proof of work. So.
It is worth mentioning proof of stake kind of arose in the cryptocurrency and blockchain space as a way to simulate a miner digitally as a kind of a replacement for proof of work, which is this way that like traditional cryptocurrencies work by like using a lot of compute power to produce a blockchain that shows that more compute power was used on that chain than anywhere else. So initially, proof of stake was about showing that more coins were used in a particular history than anywhere else. But since then, research has come a long way, and we realized that like proof of stake is a much more broad concept than just like simulated proof of work.
And in terms of when we're talking about consensus that's supported by proof of stake, what trade-offs do each of your respective protocols make in terms of aliveness and safety?
So, that maybe jumping off from what Vlad said, many similarly to proof of work, many of the initial consensus proof of stake consensus algorithms like NXT, for instance, or I think Peercoin use something similar. They really favor liveness. So blocks are produced at all times, and if different peers get disconnected on the network, then you can have two different forks, and then afterwards they might reconverge with each other. So safety is this property where everyone on the network sees the same thing and agrees on the same thing. So this is not conserved, but at the same time, at all times, blocks are being produced similarly to proof of work. While the consensus algorithms that came more from a more traditional BFT consensus literature, they usually favored more of the safety. So they always ensure that everyone agrees on the same thing. While if there is not enough people to agree on something, the network would just stop, or the particular process would just stop. So some of the kind of new approaches to blockchain consensus, some of them also try to go a bit in that direction, where under certain circumstances the network doesn't progress if there is not enough participants to achieve consensus. So, but just outlining, I guess, from our side, but I think from the perspective is similar with a bunch of different projects, is that I think it's very important to maintain some of the original characteristics of Nakamoto style consensus. So basically be able to maintain liveness in most cases, but at the same time enable the network to achieve so-called finality, or kind of be safe from a certain point on as soon as possible. So I think the most interesting approaches are the ones that kind of try to get the finality as soon as possible, but at the same time are able to be live and produce blocks.
Maybe so, like what we are working on with Tendermint, we clearly prioritize safety over liveness. And like one of the nice trade-offs there is that if you prioritize safety over liveness from like developer perspective, from an application developer that builds on top of the consensus level, is your application never has to understand how to like deal with reorgs, like which is especially like imagine you're like a sort of like an online shop and you accept transactions. If you prioritize liveness over safety, you often case have to like expect that under certain conditions you may have reorgs that sort of invalidate some old transactions you have, or that invalidate transaction you've seen before. Whereas if you prioritize safety over liveness, you only ever see things that are guaranteed to never revert, which like makes reasoning about the applications you build on top of it way easier.
Go ahead, Carl.
Okay, so in a lot of the Casper family protocols, there is still this maintenance of the kind of original liveness properties of blockchain, so that there is a path for, even if there's a bunch of validators that go offline, for the chain to not just completely halt. Maybe it slows down. That's something that can be hard to get around, but that there is still some forward progress. And in fact, sometimes the weighting of actual validators is shifting as this forward progress is made. So you can actually kind of rebalance if someone goes offline permanently, for instance. You can kind of fork the network over time automatically. And so the part of this, I think, is that there's a real kind of gradient of security that you're going to get with any like forkable history. And really every history is forkable, right? You can choose different paths down this history. And so with a lot of these consensus protocols, for instance, in the kind of more recent Casper designs that actually tie into sharding, what we have is we have different levels of economic finality at different moments in time. So once you sign the message, that's a little bit of evidence that will be included in the history. And then once it's included in a shard block, that's more evidence. And once that shard block is included in a crosslink, that's even more evidence. And then once that crosslink is included in a finalized checkpoint block, then that's like the most finalized, most safe version of your transactions history. So it's like to expose the developers and expose people to the most options. What we have been trying to do is really expose that whole gradient of security. So you actually do get you get a little bit of security at first, and then you get the really safe stuff at the end. And maybe there's a time when you can't actually get the full safety, when maybe one third or more of the validators are offline, but you do get access to this. So it's not just like black and white, safe or not safe. It is kind of a full spectrum.
I'd just like to point out a couple more ways that it's not so black and white. So in some way, the blockchain, by not having finality, means that it never makes any decisions, which means that actually it's always safe and never live. It's kind of the opposite story that we were. But if you add decisions, then all of a sudden the blockchain is like if you say decide not to revert after 6 blocks, then all of a sudden you have like a consensus protocol that's like absolutely live. But like not asynchronously safe. And so if you were to use the blockchain in the way that people actually use the blockchain and pretend it's immutable after some height, then it is a consensus protocol, and it does favor like liveness over safety. Another kind of thing that I think is interesting here isn't just the finality or not decision, irreversible decisions or not, but the best case overhead of these protocols. Because so here's my kind of like hypothesis and belief that blockchains are basically the branch prediction of consensus protocols, and can achieve like significantly lower overhead than traditional consensus protocols by being in the optimistic case where the fork isn't reverted by kind of an unpredictable message arrival order. And so I think that the overhead characteristics of blockchain-based consensus protocols and traditional consensus protocols are quite different. The latency on traditional consensus protocols tends to be lower. The latency to finality tends to be lower. And so there's this trade-off where if you want to have better overhead, you have to accept higher latency. And that's, I think, one of the main trade-offs that every project faces.
Yeah.
And the only kind of hack to get around it, which I don't consider to be that legit, is to sample nodes. Yeah. And to call it statistical evidence of the fact that you have a Byzantine form.
in general, kind of this consensus process consists of the nodes having to message each other or exchange certain information. So the more information we enable those nodes to exchange, the sooner we'll get the finality. But then at the same time, then we might end up having to wait a long time for those nodes to communicate. So there is always this trade-off: how much kind of communication do we allow before we make some progress, and do we have how much is there a possibility for gradual change in kind of confidence, and how much you kind of require certain threshold before you move on with trying to move on to the next block, let's say.
Could one of you or multiple of you please contrast the security properties of a proof of stake protocol versus with proof of work?
Sure, happy to. So proof of stake and proof of work are quite fundamentally different in terms of the consensus protocols that they allow. So like, I mean, the traditional proof of work consensus protocol, you start at the genesis block and find the chain with the most work, and it will never be able to make decisions because it never is aware of how much hash power there actually is. There could always be more hash power that shows up and reverts things. And it's therefore a fundamentally synchronous consensus protocol. It kind of relies on bounded hash rates and bounded network propagation times. Proof of stake protocols, on the other hand, can have asynchronously safe consensus, because if you know all the validator set, you can kind of tell if they've agreed to some level of fault tolerance just by looking at messages and not knowing anything about timing assumptions. In proof of stake, we have like more evidence about like what the validators do, and so we can notice if validators are censoring. Whereas like in proof of work, you can't ever tell if they're missing. So I think those are some differences. I'm sure that some are escaping me right now.
So kind of like a simple, like there's many differences, and it's kind of very hard to just simply contrast. But from like simple, maybe simple and comparison perspective, in proof of work, we kind of rely on the fact that people that burn lots of electricity and pay for this electricity really want to get a block reward, so they try to propose a valid block built on top of the longest chain and make sure they release the block fast so that it gets included and they get their block reward. Otherwise, they lose the money that they used to burn the electricity. And in terms of proof of stake, rather the parties submit a certain amount of security deposits. So rather kind of than burning this money, they kind of put it up there. And if they did something bad, something that is not according to the rules of the protocol, then this security deposit can be taken away from them. So that's maybe from a high level, like here we put down the deposit, here we burn some electricity, and we get to gain something from it or not.
There's also this kind of long-range attack problem. Were you going to talk about that?
Oh, I mean, no, but you got it.
Where basically, like, you might be, in proof of stake, there's this possibility that the signatures that you see on blocks are from validators that no longer have deposits, and therefore are not economically secure at all, and they could have been paid for like a few dollars by like anyone, assuming that people are like rational and willing to sell their keys after they no longer have coins on them. And so in proof of stake, it takes more to like establish the existence of incentives than it takes to establish the existence of costs in proof of work. But the benefit of like accepting that like, we're going to need to know who's bonded now in order to authenticate the consensus now and like learn who will be bonded later, is that we get to have like asynchronously safe consensus protocols that have stronger equilibriums and more security from censorship and reversion. And so somehow like there's a lot of engineering gains, but there is some cost to the user experience, because now you need to actually, when you use the blockchain, you need to know that like your client has the correct information about who has deposits now, because otherwise you might be subject to this attack of relying on signatures that aren't from parties that are currently incentivized.
Yeah, I mean, in proof of stake, fundamentally, instead of putting hash rate, people put up cryptographic keys to which other people, or which they themselves delegate coins to. And these are essentially the security deposits. I think, like, ideally, I mean, we could start solving this, like, long-range attacks by, like, forcing people to reveal keys, for example. So, like, that's like...
How does that solve it?
Actually, I guess from a client perspective, it doesn't. Or, like, to incentivize people to rotate keys, and, like, if you can get sort of, like, proofs of deletion of keys, not to reveal, but rather to, like, have in-protocol incentives that...
Yeah, but proof of deletion doesn't exist, right?
Trusted hardware.
SGX solves everything.
Oh, SGX, yeah, of course. Oh, I'm surprised I didn't think of that. Yeah.
So, I was in a proof of work versus proof of stake debate with David Vorik a few months ago, and it was great. It was awesome, and there were a few uncontroversial things that were differences between them. And one was definitely the long-range attack. That is a downside of the user experience for proof of stake. Another thing was the proof of stake protocols. There's kind of a larger design space because you're working with incentives and you're able to kind of gather more information, just like Vlad was saying. We can like detect censorship much better. We can, for instance, detect if there are two forks that arise and both get finalized. But the good thing is that extra kind of design space, that extra information that we're able to take in, allows us to design more incentive-compatible protocols. So we're able to do things like really penalize validators for misbehaving and kind of react to a broader set of circumstances. But that does mean that we have a more complicated specification. However, what Vlad would say is that we also do get a bit of a less complicated analysis of our consensus protocols. So there are definitely trade-offs, but proof of stake, I think, is super fun and super exciting and makes a lot of sense for future blockchain.
Also, we have
and Ethereum specifically.
And Ethereum specifically based on our design.
Also, we have a much lower like ecological cost to proof of stake than we have to proof of work. Yeah. Which is like a major benefit that I think we often forget about.
Yeah, and being in the weeds in the cryptocurrency space, like it's not a very popular point, but like definitely in broader society, people care that cryptocurrency wastes so much electricity.
And if
there is still time value of money, and we don't know exactly how much capital we'll need to lock up to get those things secure. But also one thing that the long range attack originates from is that the fact that in a way work is a kind of more objective and fundamental thing that everyone can check, and once it's done you can kind of prove that it was done, and those proof of stake algorithms kind of the incentives originate within the protocol itself. So it's kind of it's in a way sometimes hard to also bootstrap those protocols and start those protocols because the protocol needs to already run in order for people to even value the tokens that are part of the protocol in order for the protocol to be sound economically. So while with proof of work you can start with high enough difficulty, and then you can ensure that people actually do the work that they need to do. And whenever they did it 3 months ago or they do it now, it's always the same work that they did, and they can prove it.
But like with regards to long-range attack, like in theory it's a massive attack, but in practice I would actually argue that if you have reasonably long unbonding periods, it actually isn't a huge issue anymore, because like imagine you have an unbonding period of let's say 3 or 6 weeks. Like I as a client have to come online once every 3 weeks to actually like see all the updates on who is going to be in the next in the next period of bonding. And so this means like I think it's realistic that most people nowadays come online once every 3 weeks.
3 months
or
maybe.
3 months.
Or 3 months.
Yeah.
Like we can play around with these unbonding.
Make them long.
And like the only thing you initially need to bootstrap it is like some social consensus. So you could talk to, let's say, like 5 people in this room, like 5 disjoint people that each provide you the validator set hash, or like who's currently bonded. And as long as you can like be reasonably certain that you have some sort of security around that, I think most people will be fine against long-range attacks.
I mean, if you defend against them, you're fine against them. Yeah. Totally. I hope it'll be easy, and I think it'll be easy. I trust that people will be able to do it, because it's like way easier than like public key authentication in PGP, because like there's just one at any time, and so like it's a much lower burden.
Actually, also under the assumption that like there may be one proof of work chain surviving in the long run, we can always like checkpoint the latest like validator set into the proof of work chain so that people can just like follow the proof of work chain.
But they'll need to like you need to have like a protocol to make sure that like it's valid and all the rest of it.
Yeah.
Okay.
It requires engineering, I agree.
We can layer proof of work and proof of stake in our consensus protocols. They're both great.
But let's not do that. Let's just stick to proof of stake.
Explore all design.
And with research.
Yes.
Lots of research.
So with proof of work, blocks are proposed by the miner who solves the computation first. In proof of stake based consensus protocols, how does leader selection or block proposing work?
It sort of depends on the underlying consensus algorithm. Like one way is just to do a round robin essentially. So you do stake weighted. So like you do stake weighted round robin where you just you just pick the next highest person in that round robin to be the next proposer. If he times out, you just move on to the next person. You just keep going in that fashion.
Yeah, I love the round robin, but people also come up with sophisticated mechanisms to come up with random numbers to elect people, and there's usually a trade-off between a kind of unpredictability and the ability to like audit everything and make sure that like that people made blocks when they were supposed to. Although thankfully with like deterministic like pseudo-random numbers and like pre-commitments to all the seeds, you can reduce this loss of attributability quite a lot, almost completely. But there's always like ends up being like some edge case that like where like a little bit less evidence is produced because you use non-determinism in the protocol. But for the most part, people would like to do simulated mining, selecting people randomly, leader election. People like leaderless consensus protocols too, although those are a little more rare to see.
Yeah.
I think they're like less efficient than the proposer-based ones.
Maybe like one of the trade-offs actually between like the random leader selection and the deterministic leader selection is that if you do the random one, since you don't know who the next proposer is going to be, it's extremely hard to start DDoSing that person. So like if you have a round robin system, you sort of know like a bunch of steps in advance on like, oh, that guy is going to be the next proposer, and I really don't like him because if he times out, he's going to lose some amount of reward. So you can like start DDoSing him a couple of rounds in advance before he ever becomes a proposer, and you don't have that. So it's like sort of a trade-off between randomness and non-randomness.
But proposer doesn't have to be identified as a physical node, rather as a for instance, a public key. In that case, it might be hard to.
You can build a bunch of DDoS protection around like your validators.
Yeah, and they don't need to listen and broadcast on the same channels either. Yeah. And so there's a lot you can do to make sure that your blocks get out.
And another trade-off I think that is there. Vlad maybe touched a little bit on it, but kind of especially with proof of work, the type of algorithms, there is oftentimes many blocks are proposed in parallel, and then a single chain is resolved. And with kind of some of the more kind of the proof of stake algorithms that are often developed now, you have a single leader that proposes a block. And the issue is if you choose only a single participant to make a block, then if they are not online or they are malicious, they might not release a block, and they have to wait around for the next person. So actually there is some, and at the same time, if you have everyone proposing the block all the time, then you have to do a lot of work for those people to communicate. There is lots of network overhead in order to figure out which of the blocks will be actually canonical. So one interesting trade-off you can make is to actually pick a few people to release a block, so that even if a few of them will not release one, you can still make progress, while you don't have as much work to be done in order to pick only a single one of those down the road.
What you can do on the proof of stake side though as well, like these timeouts are generally not huge. We're talking about like maybe a second or two, maybe up to 5 seconds. But the nice thing on like the top level proof of stake part, you can actually like disincentivize not being live anymore. So like if for some reason you go offline and you miss, let's say, 50 out of 100 blocks, like your signatures weren't in 50 out of 100 blocks, you just get unbonded. So you drop out of the validator set, and at the same time, the protocol can now slash you, let's say, by 1% or something. To like make sure that people have an inherent incentive to always be online, always be proposing, to sort of mitigate people just like randomly going offline.
Yeah, totally. Like pretty much all we were talking about here was the distributed system stuff. But absolutely, incentivizing liveness is something we're super interested in, and we expect everyone to have an incentive to be online.
Yeah.
All the time.
Yeah. And how do your consensus algorithms deal with Byzantine actors?
With Byzantine fault tolerance.
What's that?
50% cut.
Byzantine fault tolerance is when you can tolerate the Byzantine faults. And Byzantine faults are like arbitrary behavior.
Yeah.
So there can be many.
One example of like a Byzantine fault is to sign the same block. So you have one cryptographic key to which some coins are staked. And if you ever sign 2 separate blocks at the same block height, that would, in most consensus protocol, that's considered a Byzantine fault. Because that essentially could lead to a situation in which you never converge onto a single chain. Just as an example.
But kind of generally speaking, we can divide the types of faults in many different ways. But the simplest split is between the faults that are easy to prove and anyone can prove them, and then the other type of faults which is very hard to prove and very hard to kind of come to consensus about. So the types of faults that are easy to prove, like most proof of stake systems just slash, and you just need to submit the proof once, and then everyone agrees, can check the proof. So for instance, double signing is one example where you signed on 2 different forks, or you sign something invalid that can be easily slashed. But for instance, if you were not online, then some nodes might say you were online, some nodes might say you were not online, and now we have a bigger problem. How do we actually what do we do with the nodes that there is a mixed opinion about? And this is where things like liveness comes in. So those 2 types are interesting.
And then like the second type, I kind of know about 2 varieties, I think, maybe 3 varieties. One of them is the ones that are indistinguishable from network latency. There's like whenever there's any non-determinism in the protocol, and you have to like non-deterministically choose, like so you're supposed to choose uniformly randomly between like 0 and 1, and you pick like with a other distribution. And then that's like super hard to attribute. And the other thing is that you didn't send data somewhere you weren't supposed to. And like those 3 things are kind of like the 3 things that I have right now in my mind that are like fundamentally impossible to attribute.
Yeah, this is actually like one of the most important crypto economic concepts that I think I know of. And so you have the uniquely attributable faults. Those are pretty easy. We know exactly like who did what, and we can slash them completely or whatever we want. And then the non-uniquely attributable faults, and these are super duper scary because that means that there's maybe there's 2 parties and one of them did something wrong and we don't know which one did it. And so what ends up happening is we oftentimes have to slash both of them or like penalize both of them because something went wrong, something bad happened. 2 people are one of 2 people are responsible, and we just need to disincentivize it in general. So we have to reduce both of their rewards. And what that means is now we have this thing called a griefing factor. So if you know that you can cause a fault that would cause someone else to look like they caused a fault, then you can intentionally penalize yourself in order to reduce the payouts of the other actor. And this is absolutely terrifying and horrible because it means that you can now discourage other people from participating in your crypto economic mechanism in the first place. You say, I'm going to take a hit, but I can withstand the hit, and so that you're going to lose money. And so this actually happens in the real world. I was in this economics mechanism design conference, and he was talking about like Amazon, for instance, lowering their prices to a point where they're unprofitable just to weed out competitors so that they can then raise their prices later on. So they discourage it. And so this is the discouragement attack, one of many crypto economic mechanisms which needs to be explored.
Awesome. Thank you guys so much. On that note, yeah.
Oh, wait. I don't want to clap for myself.
That's illegal. This like predator pricing is most.
Yeah, predator pricing.
Yo.
Yeah.